On this episode, we're going to talk about series parallel circuits and kind of how to get around calculating certain things, voltage, resistance, and current in these types of circuits. They're a little bit trickier than just a normal series or parallel, but we can actually use that information from both of those circuits to be able to combine them and be able to calculate and figure out those things in a series parallel. So again, let's go ahead and get started. As usual, we're going to go up here and get our voltage and our current and resistance. And again, Ohm's law, V equals I times R. Okay, so what exactly is a series parallel circuit? Well, as I'm drawing this, I'll try to explain. So we'll chew bubblegum and walk at the same time. So as per usual, we'll have our battery source, our voltage source, which is our battery. All right, and a series parallel circuit is exactly what you would think it is. It's a circuit that is part series and part parallel. So what does that exactly look like? Well, we come out here with the wire, we have a resistor, and we come in here now and it branches off into parallel. Like so. Now this is obviously just one example of a series parallel circuit. They can look a little different than this or come in different configurations. I'm just doing this as a quick little example. So here we have our parallel circuit. We are familiar with what that looks like, right? The branch of our electrons can come through here and it can go to this top branch here, or it could come down and go to that branch down there. All right. However, this parallel circuit is going to be working in conjunction with this particular resistor. This resistor is in series, okay? So this is like number 1, and it's in series to down here, okay? So we have to calculate this, again, slightly different than we would normally do. So the best way to tell you how to get in here is we actually have to kind of combine some things together in order to figure out the calculation. So in this case, it's going to be a lot easier for me to combine the resistors theoretically in this parallel circuit to create a single resistor like so. Okay, so how exactly, again, do we do that? Well, let's go ahead and throw some numbers up here, just so that way we can figure this out. Let's say this is 2 ohms, and you know what, we're going to keep this really simple. We're going to say 3 ohms, and this one is 3 ohms. Okay, now in this case, again, we're only looking at the parallel end of this particular circuit. So if I was just going to do this by normal means, I would come in here and just say, okay, what's my total resistance in a parallel circuit? Well, this is going to cause us to create a new formula, or not create one, but to show you a new formula. Alright, and if we only have 2 resistors, this is pretty straightforward. We just take R1, multiply it by R2, and then what we end up doing is taking R1 and adding it to R2. Okay, so R1 is 3, R2 is 3, and then we divide that by R1 plus R2. So in this case it's 9 over 6, or easier said and done, 1.5 ohms. Okay, so what does that mean? It means that if you were to, in theory, take the total resistance of this parallel circuit, okay, it would have a total resistance of whoops, let me try that again, 1.5 ohms. So it's like having a single resistor that has 1.5 ohms, okay? So again, let me go ahead and erase this part and erase this as well, just so that way we can have some room to be able to draw this back out. Okay, so I'm going to go ahead and redraw my circuit, but in this time I'm only going to draw it as a series circuit. So we have our first resistor, and then we have our second resistor, and then we got our ground. So again, drawing this out, this has 12 volts. We have our 2 ohms. That has not changed. This one here, even though it is a parallel circuit, we're going to say the total resistance for that particular section of that circuit is 1.5 ohms. Okay, now we can calculate our total amperage, or our current, for this circuit by just going in and calculating as if it was a series circuit. Alright, so in this case we want to find I, or the total I, equals V, which is going to be 12 volts, divided by our total resistance. So in that case, in a series, we would just add 2 ohms and 1.5 ohms, which is going to be 3.5 ohms. Okay, now we're just going to go ahead and get a calculator out here quick, because we're going to get into some decimals. So we're going to go 12 divided by 3.5. So that's going to give us 3.43. That seems like it would be rounded properly. So 3.43. Okay. So let's go ahead and write that. 3.43 amps. So I'm going to write that up here. Whoops. Just to keep track of this. So again, we're still figuring out for our series parallel circuit, but you notice that I was able to do this because I turned this parallel circuit in theory into a series circuit, combining it together. Okay? And let's go ahead and delete this and delete this. Now if I wanted to, I could come in here and we could calculate voltage drop and all that sort of stuff from this circuit as well. So for instance, what is my voltage drop at R1 here in my circuit? Okay, so in this case we want to find voltage 1 equals the total current, or current, times R1. Alright, so voltage 1 is equal to 3.43 amps multiplied by 2 ohms. So our voltage drop at R1 is going to be, what is it, 6.86 volts. So that's how much voltage we are actually using up here. Let me go ahead and erase this. So if you were to take a multimeter and you were to put the lead here and here, you would see that we would get a 6.86 volts. Okay? Now that means that we only have 6.86 volts coming in at right here and right, or excuse me, not 6.86 volts. We would have a particular amount less than 12 volts coming in here and here, and all we'd have to do is take 12, because it's a voltage drop, and let's see, it's going to be 14, let's see here, 5.14. If I I did that in my head correctly. So we only have 5.14 volts coming in to our parallel area in our series parallel circuit. Okay, it's going to be important to be able to calculate that and not skip that out, because if we use the 12 volts in our total system, that's going to lead to inaccurate measurements. Okay? So in this case now we need to calculate our amperage for branch 1 and for branch 2. Okay? And again, we would just then switch over to our parallel system. So in this case we would have let's just go 2 because we're in branch 2, right? We're going to say this is R2 and this is R3 because this one was R1. Okay, so I2 equals our voltage, which is 5.14, and we're going to divide that by our resistor, which is 3 ohms. And the same kind of idea here for our third current. So we would have 5.14 divided by 3 ohms. So it's going to be the same current in both branches because our resistors are the same. So let's go ahead and bust that calculator out again quick here. Alright, so let's see, we have 5.14 divided by 3. So we're looking at 1.71. That's pretty close. Okay, so 1.71 amps. Alright, so that is going to be there. Where should I write this? We're going to go right here, 1.71 amps. Hopefully my drawing's not too convoluted here. Alright, let's go ahead and take care of this. And of course, we don't really have to necessarily calculate our voltage drop because we know through Kirchhoff's law what it should be in theory, right? So in this case, right here, we should have 0 volts. So if we have 5.14 volts going into this resistor, we should see a voltage drop of 5.14 volts. So let's go ahead and see if we are correct on that. So V2, which is going to be checking the voltage up here, which is also going to be consequently checking the voltage drop on our V3 as well, because they're the same resistor. Might not always be the case. So then we got I2, and I2 is going to end up being 1.71 amps multiplied by 3 ohms. And again, just to get our calculator out, 1.71 times 3, and again we rounded, so 5.13. If we were to actually get in here and go 1.71, right, that's technically what it was multiplied by 3, we're getting 5.139999, which is essentially equivalent to 5.14. So yes, in fact, this resistor uses up all the voltage and we have 0. Kirchhoff's law is once again undefeated. Alright, so there's a lot of stuff here in this video. Best thing to do is, if you are confused at any point here, is to pause, rewind, rewatch kind of where we calculated some things out to make a little bit more sense. Let me go ahead and erase some of this stuff so again it's not quite as convoluted as you would think. Alright. And once we do this, I'll kind of give a real quick summary of what we calculated here. That way hopefully it makes a little bit more sense. There we go. Okay, you know what? Let's erase that as well. And I'm just going to draw that. 5.14. Okay, if I was an electron, and I started off in the battery, I'm going to be coming through this wire here, and I'm going to approach this particular resistor. As I approach this resistor, I have 12 volts. I'm flowing at 3.43 amps, and I encounter a resistance of 2 ohms. As soon as I go through this resistor, and I'm on the other side of this resistor, I've dropped 6.86 volts. So I now currently have a voltage of 5.14 volts. And as I swing up, I encounter another resistor at 3 ohms at a current of 1.71 amps. As soon as I'm done flowing through this resistor, I am now then going to be flowing here and out with a 0 voltage and swinging back in through back into the battery. Okay, and the same kind of concept here. I can come down here with 5.14 volts flowing at 1.71 amps. I encounter a 3 ohm resistor. I go through that, and on the other side I again have 0 volts as I come and travel back into the battery. Okay, so R1 here is in series with R2 and R3, while R2 and R3 are parallel. So that's why it's called a series parallel circuit. And we obviously use Ohm's law there to calculate everything that we need to know successfully. So again, get into Ohm's packet. There's a couple of the ending questions in there that are going to give you a series parallel circuit. Again, a different configuration than what you would have here, but all you need to do is to look at the circuit and see where you can combine parallel circuits to make them into a quote-unquote series, or just a single resistor by finding the total resistance for that parallel circuit, and then calculating things out as if it were just a series circuit. So you pick one or the other when calculating those things. Alright, thanks for tuning in. If you got any questions, shoot me an email or join the live streams, and I'd be more than happy to answer those. Alright, catch you guys on the next one.